Hello everyone, welcome to Physics 205. So in this video, what I want to do is go over the solutions to the in-class practice on the graphical interpretation. Okay, so for the first question here, we're given this position versus time graph. Now remember, this is really one-dimensional motion, right? You can think of the position of the object as being the position along the x-axis. Okay, that's the best way to think about it. And the object or the particle, whatever it is, could either be moving forward, backward, or it's at rest, right? And the velocity tells you the direction of the movement of the object. Okay, so based on that, let's see if we can answer these questions. Also, don't forget, if you're asked about a question about position, then since this is a position versus time graph, you can read the answer directly from the graph. If you're asked a question about velocity, then it's going to be the slope, right? You need to calculate the slope because velocity is like change in position over change in time. So you need to calculate, it's going to be really the slope of the tangent line at that point. But in many cases, the slope is going to be constant over several intervals, okay? So the first question here says, what is the particle's position at 1 second? So if we go to 1 second, so right here, oops, 1 second, go up to the graph, right? Because we're asking a question about position, and I can just read off the value. It looks like it's at 3 meters. So this is going to be 3 meters. What is the particle's velocity at 1 second? Okay, so again, I go to the graph, 1 second, and what do I want to calculate if I want to find the velocity right at that instant? I want the slope of the tangent line, which is the slope of the line that just touches the graph at that point. But notice over this entire time interval from 0 to 2 seconds, the slope is constant. So if I can find the slope of that line, that's also going to be the instantaneous velocity right at that point, right? Because the slope happens to be constant. So the velocity is constant over that 2 second time interval there. Okay, so what is the slope of this line? Well, the easiest way to figure this out, I could choose, the two endpoints. So this is like 0, 4, and then this point, which is 2, 2. And I could say the slope is the change in x over change in time, right? I could work it out. But it's much quicker if we just think about this as rise over run, right? So if I start here and I want to get back to the line here, what do I need to do? I need to move down 2, right? Down 2 meters. So that's -2. That's my rise. And in my run, I need to move over 2 seconds. So the run is a +2. So -2 divided by +2 is -1. So in this case, since it was the rise was -2 and the run was +2, then my velocity is going to be -1 meters per second right at that instant. And in fact, over the entire time period, it's also the same velocity because it's constant. Okay, what about the next question? Is the particle ever moving backwards in a negative x direction? If so, over what time intervals? Okay, so what tells us whether it's moving forward or backwards? Well, that's the velocity. And remember, the slope of the position versus time graph is the velocity. So where the slope is negative, so from 0 to 2, I guess from 5 to 7, and that's it, right? From 0 to 2 and 5 to 7, that's where the object is moving in a negative x direction. It's moving backwards. So I'll write here 0 to 2 seconds, and then 5 to 7 seconds. Okay, where is the velocity of the particle the greatest? All right, so, and we're asked about velocity, right? Not, actually, did I say positive velocity? Oh, I just said velocity here. So where is the velocity of the particle the greatest? So because we're asking about velocity and it has a sign, right? We're looking for the largest positive velocity. So where's the largest positive velocity? Well, the places where it's positive are from 3 to 5 seconds, right? The slope is positive, and then from 9 to 12. Which one has the greater slope? Well, here it looks like the rise is 1, and the run is 2, so it's like a half. And here the rise is, let's see, it's going from -3 to 0, so 3, and the run is 3, so that's 3 over 3, which is 1. So it looks like from 9 to 12 seconds, right? Because the velocity is 1 meter per second. So this is going to be from 9 to 12 seconds. And the velocity there happens to be 1 meter per second. That's the greatest. Now, where is the speed the greatest? Well, the speed is simply the magnitude of the velocity. So we don't care if it's positive or negative, right? It's just the magnitude of velocity. So really, if I'm asking for the location where I have the greatest speed, I'm looking for the location where we have the greatest slope. And that's going to be between 5 and 7 seconds, right? Here, the velocity is actually, so if I go from 3 down to -3, so I'm going down 6 over 2. So my velocity is -3, but that means my speed is the absolute value of that, which is just 3 meters per second. Okay, so the speed is greatest. That's the steepest slope from 5 to 7 seconds. So this is 5 to 7 seconds. Is the particle ever at rest? Well, again, what tells us whether it's at rest? That's the velocity. The velocity would have to be 0, right, for the particle to be at rest. So what I'm looking for on a position versus time graph is where is the slope 0, right? Another way to think about it is, so between 2 and 3 seconds, right, it's definitely at rest. Another way to think about it is this particle is staying at 2 meters, 2 meters, 2 meters, 2 meters, right? It's not moving at all. So it's at rest over that interval, and also between 7 and 9. Now, you have to be a little careful. Remember, when I created these graphs, they're really idealized graphs because it's easier for teaching purposes. See how there's like these kinks here, like at 5 seconds, there's this kink. In reality, this would have to like smoothly blend into this part of the graph right here. You couldn't have this kink here because the velocity, it's saying the velocity is jumping from like a half to -3. You know, in reality, you can't just have a velocity that jumps, right? It had to be smoother. But for teaching purposes, it's easier to draw it with these straight lines, right? So we're kind of ignoring these like locations where there's kinks. So what I would say is, where is at rest? Where the slope is 0, so 2 to 3, and 7 to 9. So 2 to 3 and 7 to 9. Okay, what direction is the particle moving at 4 seconds? So I go to 4, go up to the graph. What tells me the direction? That's the velocity. What determines the velocity? It's the slope. And here we see the slope is positive. So we know it's moving in the forward direction, right? Or positive x direction. So I'll say positive x, or we can call that the forward direction. Forward direction. Okay, next. So given that same position versus time graph, let's draw the corresponding velocity versus time graph. So I need to draw all these velocities. Well, notice that they're constant over these time intervals, right? So if I calculate the slope here, we already did that, right? If I go, it goes down, the rise is -2, the run is 2, so this is like a -1. So that means the slope, or the velocity over that time interval, will be -1, like this. Then from 2 to 3, it's 0, right? The slope is 0, so the velocity is 0. Then from 3 to 5, I think we already calculated this as a half, right? It goes up 1, so rise is 1, run is 2, so 1/2. 3 to 5. So like that. Then from 5 to 7, it's going down 6 over 2, so -3. So 5 to 7 is -3. And then 7 to 9 is 0 again. And then finally 9 to 12, it looks like the rise is +3, right? It's going from -3 to 0, so +3 up and then over 3 seconds. So 3 over 3 is 1, so this is +1. So that, again, that would be the corresponding velocity versus time graph. Now notice here, this is in real life, you can't do this, right? This is what I was saying with those kinks. You can't jump from -1 to 0, right? With nothing going on in between. you'd have to like smoothly connect it. But for teaching purposes, it's easier to do it like this. So this graph actually does have these jumps here. And then within these time intervals, the velocity is constant. Okay, next. Here's another position versus time graph. Let's answer questions about this graph. So what is the position of the particle at 4 seconds? Well, I can just read it off directly, right? It's a position versus time graph. So I go to 4 seconds, read it off. It looks like it's -8 meters. So this will be -8 meters. Okay, second question. Is the particle accelerating at any time, ignoring the times where there are kinks in the graph? Okay, hint, for the particle to be accelerating, the velocity must be changing, right? So if you have a position versus time graph, remember what represents the velocity? It's the slope. So where the slope is constantly changing, that must be where you have an acceleration. And we're ignoring these kinks here. But notice here from 0 to 3 seconds, see how the slope is like basically at the beginning, it's almost 0. Then here, I'll even draw on some. So it's like 0, and then it's negative, and then more negative, and then more negative. So if I just draw the slope of those tangent lines, more negative, and so on, it's changing, right? From 0 to 3 seconds. So that's where I have the acceleration, where the velocity is changing. So this answer is going to be from 0 to, actually, I forget here. I have to be a little careful. It looks like looks like it's only from 0 to 2 seconds. It looks like from 2 to 3 seconds, this is a constant velocity, right? So this is right here, this part, this is linear. So only from 0 to 2 seconds is it curved, right? So this is going to be from 0 to 2. It's hard to see that though on the thing there. Is the particle ever at rest? Yes, definitely from 3 to 5 seconds, right? Where the slope is 0, so the velocity is 0. And also, because right at the beginning, that slope of the tangent line is 0, you could say right at 0 seconds is at rest as well. And we're going to ignore the kinks, right? So I would say at 0 seconds, and then from 3 to 5 seconds, that's when it's at rest. What's the velocity at 2.5 seconds? So let me go to 2.5, which is here, go up to the graph. So I want the slope of this line at 2.5 of this tangent line. So again, it turns out this is linear over that 1 second time interval. So what is the slope of that line? Well, it starts at -4, it goes down negative. So it goes down, the rise is -4 over +1. So it looks like the velocity is going to be -4 meters per second. So you could say like velocity at 2.5 seconds is equal to -4 meters per second. Is a particle ever moving backwards in a -x direction? Yep. It's where the slope, right, is negative, where the velocity is negative. So that's actually from 0. Right here it's moving. It's accelerating here from 0 to 2 seconds, but it's definitely moving backwards, right? Because that slope is negative. And also from 2 to 3 seconds, it's moving at a constant -4 meters per second, right? Here it's at rest, here it's moving forward, here it's moving forward. So 0 to 3 seconds, it's moving backwards. What is the velocity at 5.5 seconds? Okay, so let's say 5.5 is here. I go up to the graph. I want to calculate the slope of that tangent line, but it's just so happens that the slope is constant over that entire time interval, right? So the velocity is constant over that time interval. So let me do rise over run. So if I start here, I'm going from -8 up to 4. So what's that, 12? And then 5 to 8. So over 3, it looks like this is going to be 4, right? Slope of 4 meters per second. So I could say velocity at 5.5 is equal to +4 meters per second. And then what is the velocity of the particle at 0? We already talked about that. Right at 0, that slope is 0, right? The slope of that tangent line. So we could say the velocity at 0 is equal to 0 meters per second. Just for an instant, right? At 0, and then it starts changing. So it becomes negative right after it. Okay, now let's draw the corresponding velocity versus time graph. So I drew the picture again here. Remember, we need to figure out the slopes, right? This is a little tricky from 0 to 2 seconds because the slope is changing. So here, right, the slope was negative, 0 at 0, then negative, right, small negative, then more negative, more negative, more negative, until right at 2 seconds, it ends up being -4, right? Because from 2 to 3 seconds, this is constant at -4, right? This is the same constant at -4. So right at 2 seconds, it's -4. So if the slope is 0 at 0, that means the velocity is 0 at 0. So it's going to start like this. And we know at 2 seconds, the velocity is -4. And we know from 0 to 2, it's decreasing. So our best guess is just to draw this like linearly decreasing like this. Just draw a line, right? It's decreasing linearly from 0 to 2 seconds. And it turns out it really is decreasing linearly. That requires a little bit more math to understand why it's linear. But we definitely know that those slopes are decreasing, right? Starting 0, smaller, small negative, more negative, more negative, more negative until it reaches -4. So that's a good guess to draw it linear, and turns out it's correct. From 2 to 3, it's constant at -4. So that will be just like this, right? Stays at -4 for 2 to 3. Then it jumps to 0, right? So from 3 to 5 seconds, that slope is 0. The slope is 0 here. So 3 to 5 is going to be 0. And then 5 to 8. We already calculated this, right? Remember, this slope is +4, right? Because I went up 12 over 3, so +4. So 5 to 8 is +4. Something like that. And then finally, from 8 to 12, let's figure out this slope here from 8 to 12. So let's see, I'm going from 4 to 6, so my rise is 2. My run is 4 seconds, right? 8 to 12. So 2 divided by 4 is 1/2, right? 2/4, which is 1/2. So it looks like it's going to be 1/2 of a meter per second for that last 4 seconds. So something like that. So that would be my corresponding velocity versus time graph. Okay, and then the last graph here is a velocity versus time graph. Okay, so now since we have a velocity, you got to be careful now, right? Now it's velocity versus time, right? Velocity. If I ask you a question about velocity, you can just read it directly from the graph. If I ask a question about acceleration, that's going to be the slopes of the velocity versus time graph. And if I ask a question about displacement, remember, displacement is going to be the area underneath the velocity versus time graph, where if the velocity is negative, like here, you have to subtract that area. If the velocity is positive, like here and here, you have to add those areas, right? And that'll give you the total displacement, the change in position of the particle. Okay, so let's see if we can answer this question. So first question, what is the velocity of the particle at 4 seconds? Well, I'm asked about velocity. I can just read it directly off, right? So I go to 4 seconds, read this off. It looks like it's -2 meters per second. So let's say velocity at 4 is equal to -2 meters per second. Okay, what is the acceleration of the particle at 10.5 seconds? Let's see, 10.5, that's like here. Go to the graph. I have a velocity graph. If I want to find acceleration, I want the slope, right? So basically you want the slope of this line, like right here. But it turns out that this is the acceleration is constant over that entire time interval from 10 to 12 seconds. So I just need to find the slope of that line, and that'll give me the answer, which is also the same slope at 10.5, right? So what is the slope of that? Well, if I start at 4, I go down to 0. So my rise is a -4. Be careful going down, -4, and my run is a +2. So -4 divided by +2 is -2. So acceleration at 10.5 is -2 meters per second squared, right? It's an acceleration. Is the particle ever moving in the negative direction? Well, to determine that, it's where the velocities are negative, right? And now be careful. We're not looking at slopes now to answer this, right? We have a velocity versus time graph. I just have to look directly at where is the velocity negative? Well, it's negative from 3 to 9 seconds, right? So we know it's moving in a negative direction from 3 to 9 seconds. Is the particle ever at rest? Well, that means where's the velocity 0? And it looks like in this case, yeah, it looks like it's going to be at rest just for an instant here at 3 seconds, right, with the velocity 0, at 9 seconds, and at 12 seconds. Be careful, it's not this, right? Here, what it was it saying, because now we have a velocity versus time graph. If this were position versus time, this would be where it's at rest. But this is velocity versus time. So what this is saying is where the acceleration is 0, not the velocity. To answer the velocity, you have to look at the graph itself, and where is it 0? It's 0 right at 3 seconds, just for an instant, right at 9 seconds, and right at 12 seconds. So at 3 seconds, 9 seconds, and 12 seconds. Each of them just for an instant, right? It's at rest. When is the velocity of the particle the greatest? Again, we're talking about velocity. I can read it directly off the graph. So we don't have to look at slopes again, right? It's not position, it's velocity graph. So I'm just looking for the largest value. It looks like right here, right, is the largest velocity, like 4. And where does that occur? At 10 seconds. So at 10 seconds, we have the largest velocity. So when t equals 10 seconds, and the velocity itself is equal to 4, right, meters per second. When is the acceleration of the particle the greatest? Here, we do want to look at the slopes, right? So where do I have the greatest? I guess since I didn't say magnitude, I just said acceleration. I want the greatest positive slope. And that looks like, oh, in fact, it's the only positive slope, right? It's between 8 and 10 seconds, right? That would be the greatest acceleration. If I ask for the greatest magnitude of the acceleration, then I want the steepest slope. It wouldn't matter if it's positive or negative. I think it's also going to be that time period. So between 8 and 10 seconds be where we have the greatest acceleration. And what is that acceleration? It looks like it's like 4, right? So I'm going from -4 to 4. So that's 8 divided by 2 seconds. Yeah, it's 4. It didn't ask for that, but I'll just give it here. So 4 meters per second squared. It's between 8 and 12 and happens to be 4 meters per second squared. Okay, what is the direction, positive or negative, of the acceleration at 8.5 seconds? Is the particle speeding up or slowing down? So at 8.5 seconds, right, that's that point right there. So if I want to know the acceleration, I want the slope there. So is that slope positive or negative? So in this case, right, the slope is positive. So it's positive. And then is the particle speeding up or slowing down? Okay, so we have to think about this, right? Right at that instant, we have a positive acceleration. We're moving, right, in the negative, we have at a speed of say -2, right, around -2. And we're going to like negative 1.5, negative 1. Right? Remember, this graph represents the velocity, and then eventually to 0 here. So we're moving in a negative direction, but the acceleration's positive. So what's actually happening? We're actually slowing down, right? Our speed is becoming less. So in this case, we're slowing down. Okay, what displacement did the particle undergo over the first 5 seconds? So to figure out displacement, I'm going to need to find the area here. I guess I can like split this up into a rectangle, say a triangle, and then say another triangle here. I'll say 3. And I know A1 is just like length times width, right? It's a rectangle. So that would be 2 times 2, which is 4. Okay, meters. Now A2 is 1/2 base times height, right? It's a triangle. And it looks like the base is 1 and the height is 2. So 1/2, 1 times 2. That's just going to give me 1 meter. And then another triangle, A3, 1/2 base times height. It looks like in this case, the base is 2 and the height is 4. So that'll give me 4 meters. However, you have to be careful. Remember, since the velocity is negative here, right, from 3 to 5 seconds, this is negative 4. Right, so this is really going to be negative, right, negative 4. And then if I add those up, so my displacement, this is just over the first 5 seconds, will be A1 plus A2 plus A3. That's going to be 4 plus 1 minus 4 is just 1 meter per second. Or sorry, 1 meter. So the displacement is 1 meter. So wherever the person started, they're going to end up 1 meter further, right, in a positive direction. Okay, and then the last question is, what is the displacement? So this is 1 meter. What is the displacement for the entire 12 seconds? Well, we already started this, right? So we have A1, A2, A3. Let's split this up into another rectangle here. Call this A4. Say A5. And maybe this whole triangle, A6. Okay, so let me figure out A4. That is just a rectangle, length times width. So that would be what? 3 times 4, which is 12, but it's negative, right? This is negative. And then A5 is a triangle, so negative base times 1/2 base times height, but again, it's negative. And so this would be 1/2 times 1 times 4. So I guess it's negative 2 meters. And then A6 is positive 1/2 base times height. So that'll be 1/2 times 3 times, where's the peak of it? 4. Which I guess is just what, 6, right? 6, positive 6 meters. So now if I want delta x over the entire 12 seconds, I have to add all those areas, right? So this will be 4 plus 1 minus 4 minus 12 minus 2 plus 6. So what is that? Negative 11, negative 13 plus 6. It looks like it's negative 7, right? So negative 7 meters. So that would be my displacement over the entire 12 seconds, negative 7 meters. So basically, wherever you started, whatever position you started at, you're going to end up negative 7 meters to the left of where you started. And the reason why that's true is this object, right, this particle is spending more time with a negative velocity than it is with a positive velocity. So they're like, here they're moving forward, here they're moving, so they're moving forward, backwards a lot, and then forward a little bit again, but they're going to end up further back than where they started. Okay. All right. And then finally, let's draw the corresponding acceleration versus time graph. So what to do that, I need to find all these slopes, right? So let's see, from 0 to 2, the slope is 0, right? So here, slope is 0. So that means the acceleration is 0. So something like that. From 2 to 5, it looks like so I'm going from 2 to -4, right? So the rise is a -6 and the run is a +3. So -6 divided by +3 is -2. So it looks like the acceleration is -2 from 2 to 5. So that would be the acceleration there. Then from 5 to 8, it's 0 again. So something like that, right at 0. Then from 8 to 10, let's see, it's going from -4 up to +4. So that's +8, and the run is +2, right? Rise is +8, run is +2. So 8 divided by 2 is 4, right? So that's going to be +4 meters per second squared over that 2-second time interval. And then finally, looks like it's going to be negative something. The rise is a -4, the run is +2, so -2, right, over that final 2 seconds. So -2, like that. Okay, so that would be the corresponding acceleration versus time graph that corresponds to that previous graph. Okay, great. So hopefully that made sense. Um, it's a good technique to know how to do is interpreting graphs. Great, thanks.